So we'll try to solve one more numerical to understand how to apply boundary conditions for thick cylinder and solve for the variation of circumferential stress and the radial stress in this. So I'm giving a numerical where there is a thick cylinder, inside radius and outside radius will be given, and then for that they will give that for this cylinder I am only drawing one side of the cylinder, only a section of the cylinder. This is inside radius Ri, this is outside radius R0. Now in this problem they are giving that the inside pressure is 50 MPa. The inside pressure is 50 MPa. Okay, and no pause in this video, so yeah, we'll come back. Okay, so inside pressure is 50 MPa. Just this data is given. They will ask you to find out, draw the variation of stress. Now, can you tell me, if it is given like this, then you need to find out other three. What are they? They say that inside pressure is 50 MPa means basically they are referring to P at inside. P at inside is how much? 50 MPa. What will be the P outside? What will be the pressure outside? 0. Exactly. You guys got it right. And have they given the circumferential stress anywhere in the numerical? No, they are not given. So what you need to do is, you can't use this part of the equation. You can't use this equation here because they are only given with respect to the value of P inside. But by common sense, you knew that the pressure outside will be 0. So you can apply this equation for inside radius and then put this value as how much? 50, and you can now substitute this value of R as 180 and put this value as 0. You will get two equations. You can use those two equations to solve for A and B values, and then once you have got A and B values, then you can substitute these A and B values to get sigma C at inside. How? Substitute the value of A and B with R as how much? 150. Then you get sigma C inside. Then again you can substitute this R as value as 180 along with the values that you have found out, A and B. Then you will get sigma C outside. So like this you can solve and then draw the variation here. Okay, is it easy? Definitely easy for 10 marks. So please let us, now what is the first thing that I have to do? So is it visible here? Here? Okay. Now let us write the boundary condition here. So boundary condition. So at R is equal to Ri, what is P? What is P? 50 MPa. At R is equal to R0, do you know this circumferential stress? It is not known, it is not given. But by common sense, you know that the outside pressure will be definitely atmospheric, so which can be taken as 0 MPa. So you know this. So once knowing this boundary condition, then you can start applying this. Since both the values of P are known, you can apply in this equation 2. This equation is 1, you can apply in this equation 2 here. So sorry, let us actually not confuse. Okay, you can apply in this equation of radial stress. So shall we apply here? So P, so applying this boundary condition 1, So what is the value of P here? 50 MPa, and then it is minus A plus B divided by R square. So what is the value of R? 150. Okay, this is one equation. You can call this equation as equation 1. And then at R is equal to R0, what is the value of P? 0 MPa. So this is minus A plus B divided by 180 square. So this equation is 2. So can you solve this equation? So will you add or deduct?
Subtract.
You can subtract. You can subtract 1 minus 2. If you do 1 minus 2, if you do 1 minus 2 here, equation 1 minus equation 2, then 50 MPa minus 0 MPa. So much it will be? 50 minus 1 minus 2. 1 minus 2. 50 minus this is 50 minus A minus of minus A. It will become plus. So it will cancel out. And then plus B 150 square minus B 180 square. 180 square. Is it up to you? Okay. So here 50 minus A plus A, which cancels out, and here B can be taken outside. So B can be taken outside. You can write this as 1 by 150 square, 1 by 180 square. So 50 is equal to, so B into, so here you can write, you can take common here. So 180 square minus 150 square. What is the value of B? Usually you get B value as very huge value. 818. Any point is there? 0.1 MPa. Okay, B value you got. Now, once you have got B value, you can substitute in any of this equation. Now this 3, this value of 3 in 1. So 3 in 1. So if you substitute, okay, instead of that, try to substitute in 2 because it's 0. It will be easy. Okay, so 3 in 2. So it is 0. 0 is equal to minus A. B value is known. 3681818.1. So be careful while transferring these values from the calculator here. Whenever from the calculator, will directly use it, no issues. And divide by 180 square. So you can take this A this side. So what is the value of A? 113.6. Okay, you get a very large B value, very small, small A value. So once you have got this 2, once you have got this value of 2, so use this 3 and 4. Now what and all you don't know now? So P inside was known, so P outside was known. So P inside is how much? 50. And P outside was 0. So you could actually draw the variation like this. You should draw the variation like this. Is it compressive stress or, is it compressive or tensile? It's compressive, so it is minus. Okay. And now we should find the tensile stress, which is sigma here. So A and B values are known. R you can substitute as 180 or 150. So you can start doing it. So let us use this value here. Sigma C at R is equal to how much? 150 mm. So sigma C, so that is sigma C is equal to A is equal to S to 113.6, and then using this equation plus B is a very large value 3681818.1 divided by, so 150 square. 150 square. What's the answer? 277.23 MPa. Guys, this is very huge value because we know that most of the steels it should be around 250 to 300, but it's very close to failure. So inside this stretching is too huge. Okay, it's very close to the failure of steel. Most of this, like ordinary steel, suppose if it is actually like rolled steels which have got higher tensile stress up to 500, then it's safe. Now it has almost gone to 277. It may be around 300 or 400, which is the failure stress. Okay, so sigma C at inside you have got sigma C is to 277 MPa. So what is this sigma C outside? For that what I have to do? Sigma C at R is equal to 180 mm. So sigma C here. So then I should use the same equation 113.6. So 368181 instead of 150 this is 180 square. Then you get some answer. What is the answer?
227.23.
How much? 227, huh? 0.26 MPa. So you can always see that there is a variation from 270. I mean, there is a variation which is decreasing. So this is 227.2 MPa. So the variation is actually tensile. So you can show this. Now the arrow marks are not needed. You can simply draw lines like this. You can draw this as positive. Positive is tensile stress, and this is negative, which is the compressive stress. Okay. For this you get 8 to 10 marks. It's good, no? So these are actually straightforward numericals using Lehm's equation. So lucky that you don't have derivation of Lehm's equation. Just using this equation, you can solve this.